Welcome back to the channel. In our previous episode, we discussed the significance of uncertainty quantification and explored the essential characteristics of an effective UQ method. We specifically highlighted conformal predictors as a promising approach that fulfills these criteria, provided a mild assumption regarding the data is met. In the upcoming episodes, we will examine this assumption, but for now, let's set that aside and focus on the fundamental principles that underpin all conformal predictors by introducing a method called full conformal predictors. But what are conformal predictors? We will start with an almost obvious, high-level and informal description. Then we will use graphics and animations to understand concepts and tools that will then allow us to get to the formal definition of conformal predictors. Let's consider a regression problem where we are given a set of XY pairs. We encounter a new point with an unknown Y value. Instead of predicting a single value, our goal is to predict an interval or a range of values. Thinking about all plausible labels that can possibly be assigned to the new point, and a plausible label here means any scalar, as opposed to, for example, a vector of length 2. Note that some of these plausible labels, if assigned to the new point, will make it conform to the previous ones, where to conform basically means to be similar, or better in this context, to comply with expectations, while others will make it stand out. At their core, what conformal predictors do is to say that the new point, whose label we don't know, will have a label that makes it sufficiently conform with the previous examples. In other words, conformal predictors want to avoid standing out. Let's take a moment to pause and allow this informal description to sink in fully. Specifically, let's ponder what it means for an object to be considered sufficiently similar with the examples available in the training data. Note that typically there are multiple or even an infinite number of labels that can render the new object sufficiently conforming with the old ones. As a result, predictions must be expressed as sets. Now, let's make the first step towards the formal definition of conformal predictors by rephrasing the previous statement using the language of sets. So, our predicted set will be a set of all plausible labels that, if assigned to the new object, will make it conform sufficiently with the previous examples. To construct this set, the first thing we need is a function that measures the conformity or non-conformity of a single object with a bag of objects, where a bag is a set of objects where repetition is allowed. You can think of it as a collection of objects. Note that I switched gears a little bit and started talking about non-conformity, which is obviously the opposite of conformity, because it allows us to use distance metrics such as absolute error, as you will soon see. In the context of the regression problem, this means a function that inputs a point and a bag of points and outputs the non-conformity between the two. What are possible realizations of this non-conformity measuring function? Let's consider an even simpler regression example, where the majority of points are falling onto a straight line, but there are two additional points that are kinda standing out. Consider the conformity of any of these points to the bag of all points. For example, conformity of this point to the bag of all points. You can see that because the blue points all fall onto the line, each of them individually conforms better to the entire bag, to the pattern that exists in it, than the green or red points. The green point is kinda conforming to the pattern in the bag while standing out a little bit. The red point is not conforming to the bag's pattern at all, and it's like an outlier. This shows that different points within the bag exhibit different levels of non-conformity, and our function should be able to measure those differences. For example, when it inputs the blue point, it should output a very low value, and when it inputs the red point, it should output a very high value. One such measure can be obtained by simply fitting a line to all points, for example, the OLS line, and then using the absolute error encountered by that model for a given point as the measure of the non-conformity of the point to the bag of all points. Is absolute error the only possible realization of the non-conformity measuring function f? Absolutely not. In fact, there are better measures, but for the purposes of this video, which is to understand the foundations of conformal predictors, absolute error is just fine. Now that we are familiar with one way of measuring the non-conformity of a point with a bag of points, that is, using the absolute error, we are ready to make the second step towards formal definition of conformal predictors. How to use the non-conformity measuring function to determine if a point is sufficiently conforming with a bag of points. Note that this is a binary determination. Once we fix the level of conformity that we deem sufficient, then the point either satisfies it or not. But we cannot make that determination using the absolute errors only, because the answer depends on how well the other points in the bag conform with it. Consider a regression example with 20 different points, and the OLS line fit to them. It is obvious that the square with such a high amount of absolute error is not conforming with the bag of all points. Now, if we spread the circles further away from each other, such that the absolute error of the square remains approximately the same, the square suddenly conforms relatively well to the bag. This shows that how well a point conforms with a bag of points is a relative concept and depends on the conformity of the other points within the bag. And we need to take that relativity into account when determining if a given point conforms sufficiently with a bag of points, and absolute error alone cannot do that. So what should we do? We can think of a conformity ladder where the higher the conformity of a point, the higher it sits in the ladder. For example, the blue dot in the middle, which has the lowest absolute error among all points, conforms very well with the bag, and thus sits at the top of the ladder. The square, which is kinda conforming, but not too well, sits somewhere at the bottom half of the ladder. So, again, the higher the conformity of a point, the higher it sits in the ladder. Note that the values in this ladder are integers from 1 to the total number of points, here 20. Let's scale these values by dividing them with 20 so that everything is nicely between 0 and 1. I emphasize that our ladder shows the ranking of points in the sorted non-conformity array and not the non-conformity values themselves. To have access to those values, let's attach to our ladder a horizontal axis showing the non-conformity of each point, that is, its absolute error. So we have two axes, the vertical one showing the rank in the sorted non-conformity array, and the horizontal one showing the non-conformity value itself. Now we can define what it means for a point to sufficiently conform with a bag of points. We can, for example, say that if the point is located anywhere within the top 90% of the ladder, then it is sufficiently conforming with the bag of points. Let's recap. We have our high-level description of what conformal predictors do. They say that the prediction set consists of all plausible values that, if assigned to the new object, will make it sufficiently conform with the existing ones. We also know that sufficient conformity means, for example, being located at the top 90% of the conformity ladder. Now, we are ready to see how to use the things we have learned so far to construct the conformal prediction set. Given a test point, all we need to do is to try all plausible target values for it, examine whether that plausible value is making the test point sit at the top 90% or not. If it does, include it in the prediction set, otherwise don't, and then examine the next plausible value. Let's see this in action. Imagine the square is a test point, and the value of 3.2 is a plausible value for it, which puts the square at the top 90%. So that value should be included in our predicted set. And this is indicated by the label that is on the right side of the square. Now, I will play an animation which will show how, as we try different plausible values for the square, in other words, as we move the square up and down, its position in the ladder changes. Pay attention to how the square moves up in the ladder when it gets closer to the OLS line in the left plot, and moves down in the ladder when it gets away from the line. Also, pay attention to how the label on the right side of the square changes from include to exclude when the square moves out of the top 90% in the ladder. We can have a similar process by moving the square up. Now, as the informal description that we started from suggests, if we collect all the plausible labels that put the square in the top 90% of the ladder, we will get a predicted interval for that test point. The beauty of conformal predictors is that once you construct your intervals like this, the probability of the true label actually falling with your constructed set is at least 90%, even when the data is not IID, given that the exchangeability assumption is satisfied. Discussing this assumption in more depth is a candidate for the next episodes, but for now it suffices to know that exchangeability means that the order of X, Y pairs does not matter. We are finally ready to put forward the formal definition of full conformal predictors. First, note that the test point being at the top 90% of the ladder, as we previously discussed, means that the fraction of points that conform better than the test point is less than 0.9. Now, given a confidence level delta and n-1 XY pairs as the training data and xn as the test point, along with a non-conformity measuring function f, then for any plausible value little y belonging to the set of all plausible values capital Y, we can define the bag of examples consisting of the training data and the test x paired with the plausible value y. Then we can use the function f to measure the non-conformity between the bag and each training point, and similarly between the bag and the test point. Then our predicted set will be the set of all plausible values for which the fraction of points that conform better than the test point is less than the confidence level, and the probability of the true label falling within our interval is greater than the confidence level. As I mentioned at the beginning of the episode, the conformal predictor method we discussed here is called full conformal prediction, and is historically speaking the first conformal method developed. Its main challenge is its high computational cost. To understand this, let's go back to the animation we had earlier. Note that each time the square is moved, we have to fit a new line using the new position of the square and all the other points. The fact that a model needs to be fit for every plausible value is a computational burden. In the next episodes, we will discuss another flavor of conformal predictors called split conformal predictors that do not have this problem. Until then, I hope you have enjoyed this lesson and hope to see you next time.